It's great to be back at Strange Loop again under slightly different circumstances, but fun nevertheless. And I'm really glad Alex and all the organizers were able to pull this off. That's fantastic. I know it was very challenging. So since Alex mentioned it, yes, I was on Japanese TV for ramen, and I'll be on Japanese TV again for ramen soon. If you're interested, I can give you more details. Okay, so let's see, I'm Will. I'm at the Hugh Kaul Precision Medicine Institute at the University of Alabama at Birmingham, and these days I'm applying functional programming, relational programming, and all that. But I'm not going to talk about those things. So we're applying interesting programming language and computer science technology, some of which is actually related to things I'll talk about today, to precision medicine. And if you're interested in that, I'm happy to tell you about that. But I'm not going to talk about that today. I'm going to talk about sort of lower level issues that are maybe more strange loopish. I figure if there's a strange loop keynote, I should talk about strange loop things. Because I work on a government project, I have to have this disclaimer. Basically, the content is solely the responsibility of the authors and does not necessarily represent the official views of the National Institutes of Health, and I believe that is accurate. My brother, who's a medical researcher, just sent me this. It will remain unnamed where this came from, but let's just say it was a government website, and it was giving information, advice about writing a grant proposal, and it said, innovation. If you are either a new PI, principal investigator, or entering a new area, be cautious about seeming too innovative. Not only is innovation just one of the 5 review criteria, but there might be a paradigm shift in your area of science. A reviewer may take a challenge to the status quo as a challenge to his or her worldview. This may not represent the official view of William Byrd. This may represent the official view of William Byrd. Okay, and I would like to thank 3 people. I'd like to thank my dad, I'd like to thank Dan, and I'd like to thank Doug. So my dad, Dr. Edward Byrd, really inspired my interest in the world, in the natural world, and science, and things like that. Dan Friedman basically taught me everything I know about computation that's worth knowing. And Doug Hofstadter has been an inspiration to me since high school, and I was very fortunate that when I went to graduate school at Indiana, I got to meet Doug and get to know him, and Dan actually hired Doug, so they're good friends, and so I would like to dedicate this talk to those 3 people, and I would also like to thank Nada Amin, who's my partner in Quine, as you will see. And so Nada and I have been playing around with parts of the code for this talk. Sort of got nerd sniped reading Doug's books, and I nerd sniped Nada along the way. So thank you to Nada as well. So when I decided to think about this talk, I wanted to do something involving Doug and strange loops, and so I started reading through, once again, I bought copies of all these books, which I've read, at least part of, multiple times, and I ordered more copies. So there's I Am a Strange Loop, there's Gerda Wescher Bach, which is like almost 800 pages, Metamagical Themas, which is more than 800 pages, which are Doug's collected articles from Scientific American, and I started reading through those. I was interested to find that I Am a Strange Loop, that was not the original title of the book. The original title of the book was I is a Strange Loop, which Doug decided was a bad title, but actually I think it was a terrific title because it really gets into what that book's about and what he is thinking about. Here's a little aside. I wrote a book with Dan Friedman and Oleg Kesryov, and it came out in 2005 called The Reason Schemer, and I wanted to call it The Reason Schemer, and Dan wanted to call it something else, and the tiebreaker was Doug Hofstadter, and when Doug said Reason Schemer is better, it became The Reason Schemer. So thank you to Doug for that one. But I'm not going to talk about that book. Instead, the things we're going to talk about are more from GEB and metamagical themas in terms of sort of the low-level content. The ideas in I Am a Strange Loop, which match very much with GEB, those are very deep ideas. And when reading those books, I ended up suffering, I think, from a very bad case of UDIS, which is unintended Doug intimidation syndrome. But if you try to read too much Doug Hofstadter, it's hard to avoid this. And there are actually two types of this. Type 1 is, Doug is just a very, cultured person. He says he's bilingual, okay? He speaks a little more than 3 languages. And he knows all about music and all sorts of things like that. And so, as I was explaining to Nada, I was a little intimidated reading up about Chopin, and she said, that's not how it's pronounced. And I said, well, that's exactly my point, right? But in my defense, I probably know more than Doug does about the C Electro Breaks remix of Shabayan Records' Monochrome in the Night, sung by 3L. That's probably the greatest song ever created by the greatest singer who's ever lived. I think Doug might disagree with that, but you should check it out. It might change your life. But anyway, so that's how I sort of compensate for the type 1 UDIS is, okay, so Doug knows certain things, I'm passionate about other things, that's fine. So I can get past the type 1 UDIS if I remind myself of that. I mean, I don't know how much Doug knows about competitive StarCraft, for example. Probably less than I do. But the harder part to get past is UDIS type 2. And UDIS type 2 is when you're reading these books or having a conversation with Doug, which I've had been fortunate enough to have lunch and dinner with him and things like that. I mean, he never does this because he's such a polite and pleasant person to talk to. But if he wanted to, he could say, and what is your theory of mind? And what is your theory of consciousness and cognition that you've been working on your whole life? And I don't, to be honest, I don't really have one. So it makes it, somewhat intimidating to think about these very big pictures, like what is it to be I? What is I? So forth. And, I was going to take a shot at trying to come up with my own theory of cognition in the last 2 weeks, but I decided to not do that. And instead, I was inspired by a great talk that Doug gave at Stanford, which is available on YouTube. I really recommend this. I'll put it online somewhere on my website or something. I'll put up a page with all this. But he told this very charming story of Danny at the Grand Canyon. So his son Danny, very, very young age, maybe not even a toddler, Doug's family and some family friends took a trip to the Grand Canyon, and everyone's looking at this gigantic, majestic landscape, and Danny, who's like 1 year old, is sitting there, not looking at the Grand Canyon, but rather fixated by ants. So he spent the whole trip looking at ants on the ground, and people somehow thought that this was interesting or unusual, that he could look at ants anywhere. But really, my talk's in defense of ants, in defense of looking at ants, because I think ants have a lot to teach us. And if the Grand Canyon is the theory of mind and the theory of cognition and the theory of consciousness, it's fine to be thinking about that and looking at that, but maybe we need to spend more time also looking at the ants. And I think that there are ants that are involved in things like strange loops and self-reference and so forth that Doug talks about. And I'm going to propose that quines are the ants of strange loops. So these are tiny little things that maybe look kind of boring at first, but once you start looking deeply into them, they have all sorts of secrets, and you can explore them. And so, part of the question I have had, and not just for this talk, but since high school, when I'm trying to read something like GEB, which is talking about issues of things like consciousness and cognition and the mind, how do you get into that? You know, I mean, it's pretty tricky. And there are also things like Gödel, incompleteness theorems, and all sorts of things like that along the way, which are really, really deep. And it's kind of hard to reach out and touch some of those things, certainly ideas of the mind. In fact, Doug, as far as I can tell, doesn't think we'll ever be able to grasp full understanding of what it means to be conscious, or to what I is, that's sort of beyond our reach. But it's still such a big scale. It's the Grand Canyon, okay? And it's hard to get into. So instead, what I advocate is, first of all, I think these ideas are important and extremely interesting and fun and fascinating. And the way I think is a reasonable way to engage these ideas is through constructive play, through trying to play around with the little parts, sort of the ants of the strange loop world, and seeing how we can build up intuition and try to find surprising things. And so when I was in high school, there was a great program for the Amiga 500, if you remember that computer. It was called Doug's Math Aquarium, and it was amazing. It could draw fractals and do all sorts of really cool math exploration. And so I think that we need a different Doug. We need, like, instead of a Doug Math Aquarium, we need like a Doug's Quine Emporium or something like that. Okay, so we can really constructively explore these little mini strange loops and self-reference behavior and self-reproduction behavior sort of in the mathematical and computational world, which is at least close to my heart, and I think close to the heart of many people interested in computation and programming and so forth, programming languages. And I will modestly or immodestly propose that one good way to constructively explore these ideas are through relational programming. So that's something I've been working on a long time with Dan Friedman and Oleg Kiselyov, and now many other people, Nada, Michael Ballantyne. I mean, the list is far too long for me to give it completely, so I'll stop right there. But this idea of relational programming, which I will show you in a minute, I think is a very interesting way to explore some of the ideas. Now, one reason is the ideas that Doug is interested in are tied up in things like uncomputability or incompleteness theorems. And just like Scheme is the language for learning recursion, miniKanren, which is the relational programming language I work on, is the language for infinite loops. If you want to understand infinite loops, write some miniKanren programs and you will understand very quickly the halting problem. You will have your fingers singed by the halting problem very quickly. But it's not just things like the halting problem and incompleteness. There's also all sorts of issues of self-reference that come up in the implementation of relational programming, and more concretely, or sort of more interestingly, in sort of a constructive way, which I'm going to show you in a minute. And in particular, we're going to look at some Quine-oriented programming, and QUAP, I guess you pronounce it. And we're going to have some Quine time, as Dan Friedman would say. So let's explore some Quine time. All right. Now, normally when I'm showing this, I spend a good 15 minutes introducing you to the basic ideas of the miniKanren language and relational programs and so forth. I'm going to try to skip as much of that as possible and instead focus on sort of the main high-level conceptual ideas, which I think you will be able to get without me getting into all the details of language. What I can tell you is that the miniKanren language is very small. Basically, it has 3 core logical operators, 1 interface operator. You could write down all the operations of the language on a 3x5-inch index card very easily. You could write down the whole sort of API for the language, even with the extensions. There are a few extensions that are sometimes useful. And the most interesting program that we've written is what are called relational interpreters. So let's see. Well, okay, just to give a little more hint maybe, let's see. I will go ahead. I think I have time to show you this example if you haven't seen it already. This is an example you might have seen in Prolog if you've ever done any Prolog programming. And so let's see if we can get this. And we're going to write a little program called appendo. And forget the syntax of this language if you've never seen miniKanren. It's not so important. What I'm going to focus on is the behavior. These programs might look a little odd, but they're not super long. You could figure it out if you wanted to. Okay. And miniKanren, the version I'm using, is embedded in Scheme. Let's see. There's a lot I could say about this particular example, but I'm not going to. All right, I think we have it defined. And now I'm going to give you a simple example. So first of all, let's just look at regular append in Scheme. So in Scheme, we can append to lists. So I can say something like, I love the list I love in the list strange loop. And I can append those two lists together to give me the list I love strange loop. Okay? I have two quoted lists, they're basically data, and I can append those together. And so now I have this appendo relation. Notice it takes 3 arguments instead of 2. So we have 2 lists coming in, and then what you might consider an output list. And so now I can run a little query where I could say appendo. So we use O to say it's a relation. Sort of sounds Spanish or something, but appendo, I love, let me put in a new line, I love strange loop. Okay, and now I'm going to put in a third argument. That third argument is Q, that's our query variable. So the run one means I want one answer if it exists, and I'm going to try to fill in, or have miniKanren fill in the value of Q that will make this true. So what I'm asking is, if you append the list I love to the list strange loop, what list should you get back? And we get the list I love strange loop. Notice that list is itself embedded in a list. We'll see why in a second. Okay, so that's a very simple example of a miniKanren program or relation. Now, let's try to make it a little more interesting, because that's, you can already do that in Scheme if you want. But where it gets more interesting is if we go ahead and say what the third argument should be. So we can say the third argument to appendo should be the list I love strange loop. And now I can put in Q, the query variable, in the middle. So now I'm asking, if I take the list I love and I append Q onto it, I get I love strange loop. So what is Q? And now we see Q is strange loop. And if we want to get a little more fancy, I can say, how about we have 2 query variables, X and Y. So I want to find 2 lists, X and Y, that when appended together gives a list I love strange loop. And we can see there's one answer where X is the empty list and Y is the list I love strange loop. But we can ask for all of the answers. We could have done a run too, but here I'll do a run star. And now we can see all of the possibilities. Okay, so X can be any of these lists in the first position, Y can be any of the lists in the second position. And it turns out this is far more flexible. If we wanted to, we could do things like this. Okay, so I could say, give me all the lists X, Y, and Z, such that X and Y concatenated together give me Z. I will not run this query for reasons that, if you need me to explain why I won't run it, talk to me after the talk, and I've got a book to recommend for you. But anyway, we can do a run one, and we'll see a very abstract answer. So here we have a very abstract answer saying, if X is the empty list and Y is anything, then Z is that one thing, the same thing. So you notice we have underscore dots that represents any sort of value whatsoever. And notice that the numbers, the zeros, are the same in the Y and Z position, saying that, hey, it's actually the same value. So that's the sort of thing you can get in miniKanren. This is effectively a theorem representing infinitely many concrete values. So from that sense, you can think of miniKanren is sort of like a theorem prover or maybe a theorem generator. Okay, so that's the simple version. Now we're going to crank it up to 11. You may have seen this if you took Prolog, by the way, or read something like The Art of Prolog. You may have seen something like this. But the difference between what's done in the traditional logic programming world, something like Prolog, and in miniKanren is that in Prolog, once the programs start becoming complicated, trying to make everything as a relation where you can put logic variables representing unknown values in any position becomes hard. So what people tend to do in the Prolog world is once the programs become complicated enough, they sort of start using what are called logical side effects or extra logical operators where you can't put in any value you want in the x, y, and z position. So that's we're going to avoid that. We're going to stay purely logical at all times. And I won't tell you how it works under the hood, although that's very interesting. There's a paper by Dan Friedman and Jason Heeman. Jason Heeman had done a lot of work on something called microKanren, which shows you how to implement the basic underlying search and unification system. So if you're interested, you can implement your own version of a simple miniKanren in something like 50 lines of code. So it's worth trying. Okay, but I'm going to go ahead and show you something more complicated instead of something more simple. Instead of appending to lists to get a third list, we're going to go ahead and jump to an interpreter. We're going to go ahead and write an interpreter in miniKanren. So the interpreter itself is a relation, and we'll see what that does. So first of all, something you should know about Scheme, which maybe you've already seen this in Lisp, or maybe you've seen this in another language. In Scheme, there's a difference between expressions that represent code ready to be evaluated, like +3, 4, which evaluates the 7, and quoted lists, or quoted data. Okay, so all I have to do is put that quote mark in front of the expression +3, 4, and instead of doing the evaluation and getting back 7, I instead get back a list or a tree in general representing the computation. So I just get back +3, 4, so I have data. Now, what if I actually wanted to evaluate that data? Well, in Scheme, there's a function called eval. So I can actually take the quoted data and feed it to this eval function. Eval is basically the little interpreter for Scheme. And then I get back 7. Okay, so we can play this game between quoting and evaluation. If you read Gödel, Escher, Bach, and you read metamagical themas, you see how critical this is to issues of self-reference, issues of code versus data. You see the same sort of behavior in molecular biology with DNA representation, where DNA basically gets turned into messenger RNA, which goes through ribosome, and through the ribosome you get proteins, which are the robots, and that the proteins themselves can reproduce the DNA and things like that. So that's a type of strange loop. And this idea of code versus data, or procedures, processes versus data, is really at the heart of many of these strange loops and many of these processes, including the processes that are happening in every cell of your body every second of the day, which is at the heart of how life works. So this is a very important idea, and Doug talks about it at length, including making lots of connections between molecular biology. Anyway, this idea of quoting, we'll see in a minute. So we have eval, which is the standard Scheme evaluator, which is an interpreter, and takes a quoted expression, and it evaluates that. Great. Now, we're going to take our eval, and we're going to rewrite our own eval, called evalo, sort of like a pendo instead of a pen, and that evalo will be an interpreter which behaves as a relation. So instead of the function eval, which takes one expression and produces a value, we will have a two-place evaluator called evalo that takes an expression and a value. So let's go ahead and try it. I think I already loaded it. Let's see. Yeah, it's there. Great. That's always the hardest part. Did I load the right file? Okay, so let's try this. I'm going to call evalo, which I've already written. And if you've written an environment passing interpreter for Scheme, like a metacircular interpreter, Evaluate is actually not that tricky to write in miniKanren. In fact, you could argue that miniKanren at this point is basically a language optimized for writing evaluate. That's not too far. I mean, it's kind of true. But that's because evaluators are super important. Okay? So we're going to go ahead and have a little quoted expression. How about quote I, quote love. All right. And I'll say strange loop. All right. So we're evaluating this quoted expression. List in scheme just creates a list of arguments. So we have quote I, quote love, quote, I need to put quote in front of strange and loop. Okay, so we just have a list of quoted symbols that we're putting together. And if I run that, I get a list containing the list I love strange loop. All right, that's not very interesting. Just to show you that this is the real deal, if I take the unquoted expression and just run it in Shea scheme, I get back the same list. Okay, I don't get a list of lists because we're only getting one answer back in Shea scheme, but it's the same idea. Now, let's go the other way. I will take the list I love strange loop, and I will put that in the value position instead of in the expression position. And so let me write this expression, this query. So here I'm saying I want an expression in the subset of scheme I've implemented that evaluates to the list I love strange loop. I want one such expression if it exists. Let me try it. Okay, I get quote the list I love strange loop, which is true, but not very exciting. So let's try doing 99. Okay, this is maybe more interesting. Okay, so here, let me grab one. Now there's some side conditions down below I'll ignore for now. And this is a little hard to read. So if I wanted to, these underscore zeros and underscore ones and underscore twos represent sort of abstract values because this is really a theorem. But you can see there's a call to list with no arguments, which produces the empty list. We have a function call here. We have a lambda. This is effectively a let expression. And so I run that, and sure enough, in Shea scheme, it produces I love strange loop. So we can start playing these games. All right. Now, the next expression, the next parlor trick we're going to play is, what if we wanted to generate an expression in scheme, or a subset of scheme, that evaluates to itself? What would that query look like? We want an expression that evaluates itself. Yes? Evaluate EE. It can't possibly be that simple. And yet it is, once again. Okay, so let's grab this, and I will run it, and we get back the same expression. And if I change the, let's see if I can do this. If I change the underscore 0 to x, all right, just to make it a little easier, I'm basically instantiating the variable name, then that is sort of the canonical Quine for Lisp or scheme. Okay, so I use the word Quine. So this is a program that evaluates to itself, which Doug Hofstadter in GEB coins as a Quine after the mathematician Quine. And notice the use of quote. Notice the use of evaluation and the use of quote. Very important. And as Doug points out, this is similar in a way to what's going on at the molecular biology level and so forth. And we've got strange loopish behavior starting to become manifest. Okay, let's try doing something a little more aggressive. So that is a quine. This is an expression that generates a quine. Let's generate twines. So twines are twin primes. Okay, so twin primes are primes P and Q, or quines P and Q, such that P evaluates the Q and Q evaluates the P, and they're distinct. Okay, so let me try to write that. So we have P and Q. You P evaluate to Q. Q evaluate to P. All right, so is that the right query? Or do we need to add something else? Okay, we need to say they're distinct, right? And so this is the version I've been showing for a number of years now, ever since, basically ever since Stu Holloway pointed out to me and to Dan that we should be able to generate quines. I've been doing this version where I say P is not equal to Q, okay? And sure enough, we can generate two distinct programs, but these programs are actually kind of boring. Okay, as a reviewer pointed out in one paper, this is kind of boring because one version is just a quoted expression, and it evaluates the unquoted version of itself. And then if you evaluate the unquoted version, whoops, hold on a second. If you evaluate the unquoted version, you just get back the quoted version. So it's like, basically we're just adding or removing the quote from the beginning. Now, when I was starting to read these books again, in preparation for this talk, I got interested in the quines because Doug was talking about the quines in his book. And it occurred to me to try something a little bit different, which is to use another constraint that we have in miniKanren called absento, which is saying that the first term cannot appear anywhere within the second term. Okay, and so now we're saying P and Q, not only do they have to be distinct, but P structurally can't appear inside Q, or vice versa. And now when I run it, I start getting quines that are actually structurally different. So here, I've got a quine where I'm calling list on the outside, and you can see there's a bunch of quoted stuff going on. And when I run it, I get a direct application of a lambda expression. And when I run that, I get my call to list again. And so we can start playing new games here. And this was interesting to me because I guess I've been doing demos of the quine stuff in miniKanren for 10 years, something like that, maybe longer. And I just finally realized that there's this trivial change that makes the quines much more interesting. Nada and I have been playing around quite a bit with a whole bunch of different versions of quines. So one version we have is the Quine Relay, which, let's see, I might be able to show you that quickly. Okay, I'll show you the Quine Relay real quick. I actually have lots and lots of things I could show you. I've got a lot of quines I could show you, but I'm not going to show them all to you right now. Nada and I think, will post a live code for playing with the quines. But let's see if we can load the Quine Relay. Okay. All right. So the way the Quine Relay works, so this is an exploration of a simple program, a simple version, basically, of something I saw a few years ago that's much more complicated. And so the idea here is that we now have 3 different interpreters for different languages. Now, in industrial Quine relays, you might have code produced in a Python program that produces Java program that produces C++ program and so forth, and eventually it goes back and produces the original Python program. You can keep doing that. Okay, so I wanted to play around with that. The interesting thing to me was being able to synthesize the quines automatically by just giving the operational semantics for the underlying language. Okay, so we're not constructing this by hand at all. We're just asking miniKanren to produce the quines or produce the code by synthesis just from the constraints we're writing down. And so, for example, in this version, I have an evaluator that uses cons, a list constructor. I have another evaluator that has the list operator, but not cons. And then I have another one that uses quasi-quote instead of list or cons. So these are 3 different ways of producing quines, or sorry, of producing expressions. And let's see if I can, find the 3. Okay, so here we have it. Let's see if I can run it. Supposedly it takes 36 seconds to finish. So while it's running, let me try to explain. So basically, you've got 3 different interpreters for 3 slightly different versions of scheme, and they're different in the list operations they handle. So they're not as different as Python and Java, but hopefully you sort of get the point that we have 3 different interpreters that have different languages. And so the eval quasi has quasi-quote operator, if you're familiar with that, but it doesn't have cons or list. And then conso and listo have cons and list operators, but not the other operators. And so now here we have a little Quine Relay program. So if I can find the start of it, let's see, here we go. So the first one, let me make sure I'm running this correctly. Okay, so the first piece of code we have is quasi-quoted. So that's the back quote or quasi-quote. So this is almost constant data. And if I run that, then I get another expression that uses cons, but without the quasi-quote. And if I run that, then I get another expression which makes use of list, but which doesn't make use of quasi-quote or cons. So now we're getting into much more sophisticated behavior, self-reproducing behavior. And the interesting thing to me is that this is all based on encoding an operational semantics for the underlying language as an interpreter, and then having a constraint system with search and various types of constraint solving to automatically figure out what the behavior is. Okay? So this is what I mean by a constructive way to play around with these ideas with quotation, interpreters, Quine, self-reproduction, and so forth. Nada and I have a whole bunch of examples also with more sophisticated self-reproduction, sort of like the von Neumann self-reproducing machines, universal constructor type programs, and various types of virus behavior that Doug talked about in his books, but I don't really want to show any virus stuff this year, so that's not, I will put that online, but I'm not going to talk about it. Okay, so I could show you a lot more Quine-ish and self-reproducing behavior, but let me make some strong claims now. So this reminds me of the Danny at the Grand Canyon story, and if you take that story seriously, and you think about what's going on with those ants, Danny is looking at one ant by the Grand Canyon. That ant has a bunch of cells in it. In the gut of the ant, there are other types of cells which aren't, what we might think of ant cells, but they're cells of bacteria in the gut of the ant. And inside that bacterium, in the gut of the ant, is a constant war between viruses and other sort of bacteria which are trying to exchange genetic material with, say, an E. coli. And one of the amazing things is if you look closely enough, you'll see in the bacterium, and many species of bacterium that have a circular genome, that there are these clustered, regularly interspersed palindromic repeat areas of the genome, of the DNA sequences. And it took a long time for people to figure out what those are. Well, what those are databases that are dynamically updated that contain basically DNA snippets from previous attempts at viral infection or from other bacteria trying to exchange genetic information. And it's actually a defense mechanism against viral infection. So maybe you've heard of CRISPR-Cas9. So Cas is CRISPR associated. Cas9 is one of the proteins produced as part of this CRISPR defense mechanisms. There are other proteins, there are 2 proteins that we know of at least, that actively maintain this CRISPR database of genetic sequences of from viral infections, attempted viral infections. And there's actually a FIFO queue, the first in, first out queue that gets actively maintained in the genome of a bacterium. And it turns out that even though we aren't bacteria and we aren't viruses, this mechanism, this CRISPR mechanism, which is very powerful, can be used to modify DNA, and as you may have heard, now can be used to modify DNA in humans, and there are ongoing clinical trials in humans to try to fix up problems with DNA, genetic-based diseases in humans. In fact, at the Hugh Precision Medicine Institute, this is very relevant to what we're doing. So when you have Danny at the Grand Canyon staring at an ant, if you zoom in enough, you've seen the same cellular processes that are happening in Danny, and if you zoom in even further, you see this CRISPR defense mechanism, which can now be used to treat humans. And so it turns out that Danny, I think, was right to look at the ant after all. And similarly, I think, with behavior like Quine's and small self-reproducing programs, there are a lot of very interesting things that, if we uncover them, I think will have bigger implications. So I would like to defend TAS, which is taking ants seriously. And you can think of the ant industrial complex, or like I like to call it, big ant. And quines are the ants of strange loops. So we should think about taking quines seriously, and I mean really seriously. And so big quine industrial complex. And if you've heard of MIPS, which is either millions of instructions per second or meaningless information about processor speed, or LIPS, which is logical inferences per second, I propose that we have a new measure, which is QUIPS, which are quines per second. And so we could have quine, well, maybe not quine coin, that might be a bad idea, but we could have an exaQUIP supercomputer. And if we want to reach the stars, like in StarCraft, if we want to meet the Tal'Darim and get their terrazine gas or whatever, or if we want a theory of consciousness, then we really need to get very, very good at understanding these very small, strange loops that are at the heart of things like quines or viruses or self-reproducing behavior. And as Teller, the magician, says, sometimes magic is just someone spending more time on something than anyone else might reasonably expect. I think we need to spend unreasonable amounts of time studying quines. I don't think that's currently being done. So I'm going to propose, I'm actually going to start the QUIPS prize. So I will give $1,000 a year from now to the best type of self-reproducing behavior in this constructive manner. And if Alex allows me, I'll even I'll award it at Strange Loop. And so that's the web page. I haven't yet put up the exact rules because I need to figure those out. And so this is the very small strange loops, okay? And I think we need to take them very seriously. There's one other thing I want to talk about, which I didn't have time to prepare for because I think this is going to be a much bigger effort, is John Doyle, who got his PhD at the MIT Artificial Intelligence Lab, I think in the early 80s, has some amazing work. One is on truth maintenance systems, argumentative TMSs that are communicating with each other. And then his PhD thesis proposal was on communicating reflective metacircular interpreters. And so these are like bigger strange loops. And I would say these are bigger ants. These are big ants. And in fact, they're so big that I'll call them mants, which is from, there was a great movie called Matinee with John Goodman, where it's about the 1950s horror movies, and he plays in a movie called Mant. Half man, half ant, all terror. Mant, is he man or ant? So I think this is like the Mant of strange loops. It's not quite the small ant, but it's the bigger ant. So there'll also be a $1,000 Mant prize for the best implementation or riffing on one of these ideas. In particular, I think the communicating reflective metacircular interpreters is extremely important. And something very interesting happened after he proposed this work, which is nothing. Nothing happened. As far as I can tell. And as far as I can tell, literally no one in the world is following up on these ideas. This is probably the best idea that I've ever seen having to do with strange loops and things like that in the small. And I think there's a lot to be learned. And John Doyle was going full steam with these approaches towards real artificial intelligence. And one of the things that happens over time is that sort of people either lose their nerve or they think it's too hard. So some of these techniques have sort of made their way into programming lore, but removed from the idea of doing artificial intelligence and much more about here's a useful technique for programmers. But if you go back and read the original works by Doyle, he was trying to basically build strong AI. And even though I don't know that you could get there from here, I think there's some very powerful ideas that are extremely underexplored and are worthy of exploration. So 2 prizes, the MANT prize and the QUIPS prize for 1 year from now. And I will update my web pages with the actual rules, and $1,000 each. And if Alex allows, I'll award them at Strange Loop next year. And so we should take our ants seriously. We should take our MANT seriously, and respect the ant, respect the quine, and get to it. All right. Thank you.
I can't wait to see the Respect the Quine t-shirt. I'm ready for that one. I would be happy to have you announce a prize next year.
Great.
That would be my pleasure. All right.
And just to remind you, it does not necessarily represent the official views of the National Institutes of Health.
It's probably good to note that.
You said you haven't figured out the rules yet. Have you considered using miniKanren?
Okay, so I don't have the rules for either the MANT or the QUIPS prize, the competition. And so the question is, had I considered using miniKanren to generate the rules? No, I hadn't, but that's a very interesting idea. And one of the things Doug talks about in Metamagical Themas is this idea of a set of rules for a game that are meant to be modified or mutated, right? And I've thought about encoding that in miniKanren, and I suppose that could be something that would also, the prize rules are expressed in miniKanren, and they're mutating. So every year, we get some sort of random mutation that hopefully is survival of the fittest, but maybe survival of the fittest for my wallet, where I don't have to pay out $1,000 for each prize.
So, I noticed in the miniKanren demo of, just sort of doing code synthesis, it can generate, obviously, code for fixed outputs. Do you see any way of, generalizing that so that you could just have a constraint over the types of outputs?
Oh, for the type, using type constraints and things
Type
like
constraints or anything similar,
Sure,
maybe logical
sure.
constraints.
I normally show a lot more of that. And so we've got a tool called Barliman that I've been working on with Greg Rosenblatt and also Michael Ballantyne and other people have been helping us work on it. And now I'm working with Kanaya Tsushima in Japan on sort of a new version of it. And so that's a synthesis system designed to actually sort of be efficient enough where you can synthesize sort of interesting recursive definition from examples. But one of the ideas we want to have is to also have things like type information. So you can, the way it actually started is before this relational interpreter, there was actually a relational type inferencer. And that was something that Oleg Kiselyov was working on. And that was the first miniKanren program, or actually back then it was Kanren. That was the one that sort of blew my mind. And then I got obsessed with doing the same thing with an interpreter. And it turned out, for various reasons, doing it for an interpreter was maybe much trickier. So what I would like to be able to do at some point is have a synthesis system that combines type information, other types of constraints, like maybe you could say, I want to synthesize a function that is associative or commutative or things like that, and also give examples and maybe several other types of pieces of information, and then maybe give hints to the search and things like that, and also templates. And so some of these things we're actively working on. We're working on biasing the search based on what human written code looks like in Scheme, and also doing probabilistic versions and templated queries and so forth. So that's an active area of research. Program synthesis in general has become a very active area of research in sort of formal methods and programming languages. It's been a lot of work. Some of it is based on things like dependent types and so forth. The approach we're taking is somewhat different. And once again, I'm interested in the emergent behavior when you just write down the system of rules, what can you get out of it? So the thing that I want to preserve is the fact that we don't have a synthesis system. It's just we're writing rules down, and we have a system that can be flexible enough that you sort of get as an emergent property, sort of is inherent in the rules, but we're not setting out to write a synthesis system per se. That's what I'd like to. And that's also what's interesting to me about the Quine stuff is that nowhere encoded in any of that software or that interpreter is the notion of Quines. That came out of it. In fact, when Stu Holloway said at the ClosureCon that you should be able to synthesize Quines, I was like, oh, Dan and I were like, oh yeah, that's right. And then I was giving a talk at Indiana, and Larry Moss, I think it was, said, oh, you should be able to do Twines. And I made the joke, okay, I wrote the Twine query down. I said, I started it running. I said, no one can leave until it comes back. I assumed it would take 1,000,000 years, and then it came back after like 3 seconds, and I was kind of flabbergasted, right? And so that's the fun thing to me. This is what I mean by the constructive exploration. The fun part of it is like I can't wrap my head around, I is a strange loop directly. That's like too big. But I can play around with the smaller ideas, and maybe there's something there, sort of like CRISPR, that's useful. I mean, there certainly are things with Quines, like the SMN theorem and Kleini's recursion theorem and Smullyan's double recursion theorem. They're very important computational ideas that are used in bootstrapping compilers and that turn out to be used in computer viruses and things like that. So these ideas are very powerful, but I think that there's a lot more to learn from exploring them.
All right, thanks everybody. I assume that since nobody has burst in with guns or anything like that, this Quine challenge doesn't lead to the singularity, and they have to send people back through time to kill us. So, but time will tell, I guess. So, yeah.
We'll all be
thank you,
replaced
everybody.
by Quine.